Hello, hello, testing, testing. All right. Okay. So, is anyone here yet? No, not yet. Just waiting in the chat. Okay. Just want to wait to see if anyone's going to come. Don't be shy. We're going to get started soon. Figure out the best way to do this is to make everyone feel comfortable. Anyone here yet? Anyone here? Testing. Write something in the chat. Let's see if anyone is here. I think anyone's here yet. Okay, no one's here yet. Nope, nobody yet. All right, I'm just going to get started. So, welcome back to STEM Online Academy. For those of you who don't know what this channel is about, this channel is about advanced mathematics and physics education. So we specialize in these topics, specifically for undergraduate students in university who want to be able to enrich, either enrich or challenge themselves in things like calculus, physics, linear algebra, and so on. Our approach has always been it's a very interesting approach to doing mathematical problems, which is using pretty much a three-tier approach to problem solving. Okay, and that is number one. Number one is always making sure you have a strong foundation of the problem that you're dealing with. Okay, so what do I mean? Strong foundation also means, well, it's pretty self-evident. Making sure you have the correct prerequisites, knowledge, no gaps, and a very fluid understanding of the subtopic that you're dealing with. For instance, if it's algebra, you make sure you understand all the properties, the axioms, and the mechanics of how algebra works, right? Whatever it is. So whatever you're dealing with, you want to make sure you have a strong foundation in the mathematical or physical realm that you're dealing with. Okay. So that's step one. Step two, actually, that's part of step one. Another part of step one is not only having the strong foundation, but is to also make sure you're understanding the semantics of the problem. Okay. So what I mean by that is you want to make sure that you're actually understand what's being asked of the problem, so you're able to come up with an answer that is, coherent with the analysis. Okay. So that's part one. Part two is always transpose what you know, what the problem's asking, into a model, simulation, or graph of some sort, right? Because what that does is it helps you see in real time what you're dealing with, seeing either mathematically or physically. Physics is more important, but math too. See what you're dealing with in terms of the problem. Okay, because let me tell you why graphing or drawing or making simulations is important. It's because it can help you, one, it makes the math come alive. Okay, who doesn't want to see a nice simulation on the screen? Okay, so that's number one, is this see some interesting properties mathematically, right? I'm going to use some simulations in this live show if anyone is interested. Okay, so that's one of this, is making simulations. Okay, making simulations or models or graphs of some sort, because it makes the topic interesting. And another thing too is it can help make sense of what you're looking for, right? What do I mean by that? Classic example, let's say, for instance, you have, the area of a curve above the x-axis. Automatically, if you're looking for the area of a curve above the x-axis, it has to be positive. Okay, right? So if that's the case, you have to, your reasoning should be saying, okay, um, when I'm doing my algebra based off of how my graph looks like, I better get a positive answer after integrating under the curve, right? Because the geometry of the problem already was showing that it should be a positive area. So if my computations come out negative, I'm doing something wrong, right? And this can happen. Everyone makes mistakes, but that's a good way to compare between the geometric model and the algebra after. There should be a coherent comparison between what the geometric model says and what the computations say afterwards. Okay, so the calculations should match the modeling. Okay, and then part three is obviously, once you've done that, using a strong mathematical method. Okay, so any of the methods that you either learned in university or school of some sort, that's the easiest part, because then after it's just a robotic process. Well, not all the time. Some mathematical methods can be extremely complicated, right? But and that's what you would figure out in my part of my book. But anyways, most of the times mathematical methods are the easiest part. It's just a robotic process. The hardest parts are step one and step two, is setting up how to solve a math problem. Afterwards, when you get to step three, it's just plug, chug, rearrange, do stuff like that. Okay. All right. So let's get started here. I think what we're going to look at today. So let me just share the screen. Okay, just give me a moment to share my screen here. The entire screen. Okay. We're gonna go to let's open board if possible. Give me a moment. Okay. All right. Hope you guys can see this. Let me know if you're able to see the screen, because I don't want to keep blabbering and you guys are like, okay, he's talking, but where's the screen? Right? So please let me know if you can see the shared screen. Stop. Just 1 second. I'm going to go back here anyways. Okay. All right. Can you guys see the screen? Let me know. Let me put thumbs up or something. Give me an indication if you can see it. There should be stuff on the Fourier transform, stuff like that. Okay. Let me see if I stop sharing for a moment. Can I go back to, okay, let me go back. Desktop. Okay, what I'm going to do is I'm going to do it like this. screen. Entire screen. Let me do entire screen first. Entire screen. And then what I'm going to do is I'm going to pull up the whiteboard. Okay. All right. Okay, so looking here, you should see it right now because quite often I do it this way. So we're looking at the Fourier, we're going to look at something called a Fourier transform. Okay. And if you guys, at least the ones who have already seen my past videos, you know that I started to transition from just doing regular math and physics problems and mainly looking at problems from my book, which is Advanced Integration Techniques. Okay. I made this book particularly for students who want to master advanced integrals and applications, and also because it's part of my three-tiered approach, right? Step 3 when it comes to problem solving is implementing mathematical methods. Okay, so I thought that would be somewhat relevant to my approach on advanced applied mathematics, right? That's what my book is on. It's on applied mathematics. Okay. Okay, so today what we're going to be looking at is something called a Fourier transform. Okay. All right, Fourier transforms are interesting. They have applications in waves, sound, and quantum mechanics. Okay, that's what they're most often applied to, is any form of musical instruments. Okay, so Fourier transforms are used in musical instruments. They're used in, they also have applications in quantum mechanics. I'm going to talk about some of those applications. I just want to point out I'm not a quantum mechanics expert. I'm just saying there are applications in quantum mechanics. Okay, I'll talk about some of those applications. Okay, for expertise in quantum mechanics, I may need to, direct you to somebody else, but I will talk about the applications in quantum mechanics. Right. All right. So we'll be looking at some of these applications in the live show. Let me talk about it specifically what we're going to be looking at. Okay. So one, we're going to look at the visual intuition of the Fourier transform, as well, not just specifically the Fourier transform itself, also some functions when it comes to waves. So any type of wave type of function, we're going to look at some sort of simulation either with Desmos graphing, or another type of simulation. I go back and forth from Desmos to other complicated simulations. Usually those require coding. But anyways, so that will be one. Okay. 2 will be looking at real and complex exponentials and combining to form intricate solutions. All right. Number 3, we'll be looking at Gaussian transforms and frequency domains. Okay. So we're going to be looking at that. 4, maybe some research level problems, only if we have time. I don't know if we will. This is going to be very comprehensive. Again, don't be shy. Anyone who has background in calculus and linear algebra should be fine with what I'm talking about in this lecture. Okay. Let me know if there's anything you want to discuss. I want to see if any of you guys have any questions in the chat. Okay. Let's see. 1 second. Anyone here? Any questions? Okay, so no questions yet. Wonder if I should be waiting. I'm gonna wait if anyone else is coming. Okay, so anyone else is going to be coming here. We've got one person over here. My last live show had a person who was coming in who was an enthusiast. You don't have to be just an undergraduate student. I mean, mainly the topics that I'm going to be discussing, either when it comes to math and physics, will be for undergraduate students. But you can be an enthusiast yourself. Doesn't matter. Okay. So maybe you're learning about these topics and you're interested in digging deeper. This is the channel for you, right? Undergraduates, enthusiasts, and even some graduate students might be interested because this book pretty much covers everything in calculus 1 to 3, okay, and even a little bit of elementary complex analysis and numerical methods and etc., which lead up to almost a graduate level setting. Okay, so anyone's coming on? Okay, is anyone there? Okay, let me make sure I understand. Mm-hmm. All right, so no one yet. Okay. All right, so we're going to proceed. Let's continue anyways, right? Because I don't want to waste any time. All right. Because even for those of you who aren't live right now, maybe you're going to see this later on YouTube. So I don't want to waste time. I want you guys to see what I'm doing, in case for anyone who sees it afterwards. All right, so let's go back to the whiteboard. Okay, let's go to the whiteboard. All right, so let's get started. Okay, first we're going to be looking at a visual. Okay, this will be on another screen. So let me just get out of this. Let's go back to, yeah, let's go back to the desktop. Okay, and I'm going to reshare. All right, I'm going to reshare my screen. So let me go to share for a sec, and I'm going to reshare again. Share screen. I think I'm going to go to Desmos. Yeah, we're going to go to Desmos. Okay. You guys should be seeing what I'm doing. All right. Let me know if you guys are able to see what I'm doing. Right. So what we're going to be looking at, okay, we're going to get started off here at looking at a specific function y equals e to the ax cosine bx. Okay. We're going to be looking at this function. Right? And the reason why we're going to look at this function is because we're going to take the integral of this function. Okay, so we're going to be looking specifically at the wave pattern formation of this function. Okay, so if you can see what I have here on Desmos, y equals e to the ax cosine bx. All right, the parameters here are a and b. All right, so a and b are fixed parameters. No, not fixed. They're going to vary because I'm going to put some, I'm going to put some, changing. It's going to change whilst I'm doing this, okay? Because I can put some steps and some other stuff on Desmos. For those of you who know how to use Desmos, this will be easy. For those of you who don't, you should know how to use Desmos by now. They even do it in high school, okay? So let's look at the graph for Desmos, okay? So what I'm going to do is I'm going to start playing it. Just give me a moment. Oh, damn it. My apologies. Let me go back here, back to the desktop. Okay, so what I'm going to do is I'm going to start playing the function. Okay, just 1 second here. And I'm going to start playing this guy as well. Now, as you can see here, right, this is y equals e to the ax cosine bx. This is a sinusoidal function, right? And as you can see, this is pretty interesting. So what do you notice happening with this function? Okay, can anyone tell me what is going on with this function here? It does look pretty cool, doesn't it? Well, just like any other sinusoidal function, right? It's periodic, right? Its motion is periodic. It keeps going back and forth, right? As you can see here, okay? So it's just oscillating back and forth. That's an interesting type of oscillation. That's why I wanted to bring it up, okay? So not only is it going in a periodic motion, right? Right, they're going in a periodic motion, but What else happens in periodic motions? Anyone know what happens in periodic motions? Anybody know what happens in periodic motions? Anything else? They keep going forever, right? They have a very interesting lifespan, right? This goes back and forth, like a regular sine wave, right? The regular sine wave, y equals sine x, for instance, as you know, will just be going, you know, yes, period of 2 pi, for instance, a regular sine function, and it just goes up, down, right? Here's different, right? The amplitudes are different. So you can't really say it as an amplitude here, but you can see that the function is it grows a bit, and then after it goes down, really goes down, and it really goes up again, right? Okay. Now, how would you describe, what else can you describe about the function here in terms of the features of the graph? Anything else interesting about this Desmos simulation that you want to discuss? How is it related to let's say a Fourier transform? Okay. Why is this related to a Fourier transform? Well, it's related to a Fourier well, you can take it a Fourier transform of all sorts of functions, but I'm going to get to that in a moment. Okay, so I just want you to see the graphical behavior of the function before I start getting into some integrals. Okay, all right, so you can see a and b are varying. Okay, now what can you say about a and b, right? The parameters of a and b of the simulation that is moving back and forth. What can you say about it? Like, we know that a and b are varying. What is a doing to the stretch of the graph, would you say? Anybody know what a is controlling here? Want to take a guess? Okay, so think of it this way. Y equals e to the ax. So a is varying some sort of horizontal stretch or compression. That's what the a parameter is doing. Okay, so horizontal stretch or compression. When it comes to the function e to the x, right? That's like saying e to the ax. Let's just think of it individually. And cosine of bx, again, is doing some sort of horizontal stretch or compression here. Okay, so that's what we're mainly having, right? And you can see that's what this graph is doing, right? Like horizontally, you can see that it's stretching and compressing back and forth. So the stretch and compressions of the simulation, right? The graphical simulation here, right, is shown to be compressing and stretching horizontally, right, which is pretty neat. Would anyone say that there's a vertical stretch or compression? Or is it just purely horizontal? How do we know that? So think way back to, like, say, grade 10 math or something, right? When you graphing functions. Okay. So is there a vertical stretch? Like algebraically in this equation, is there a vertical stretch or compression? No. Now it can look deceiving, right? The wave, the wave function, you say it's some sort of wave function, right? The wave function here, our eyes are showing us that it's a vertical stretch or vertical compression, because you can see the first part here. Okay, right? This first part here that I'm highlighting. Okay, you can see that it goes from decrease to increase, right? Like vertically, right? If you pay attention to this back and forth, that's why I was playing it for a while, to show you, to see if you guys can see what's happening. Okay. So you can see that it's vertically stretching up and down, but it actually isn't. Mathematically, it isn't because there's no constant value in front of the e. If there was a constant value in front of the e that was greater than 1 or less than 1, right? As long as that value is between 0 and 1 or greater, strictly greater than 1, then there would have been a vertical stretch. Okay. Otherwise, there isn't. Okay. I know it looks like this portion here, right, is increasing, decreasing, but there is absolutely no vertical stretch whatsoever. Okay. There is no vertical stretch. All right. So that's one thing. Okay. All right. So what I'm going to do right now, I think we've got enough of that. So let's stop sharing that part. Okay, so let's go back and look at something else here. Okay. All right, just give me a moment. Okay, let's go to the desktop. All right, so we're going to be looking at the next part here. Okay, so we looked at a visual intuition of a Fourier transform. Now, this what we showed was part of a Fourier transform. Now, a Fourier transform, okay, usually has something of this nature. Okay, so one of the problems that we're going to be looking at is solving this integral e to the ax cosine bx dx. Okay, specifically, I should be saying looking at a Fourier cosine transform. Okay, all right, Fourier cosine transform, right, is something like this. Okay, if you can see that. All right, so if you look at this, okay, this is a Fourier method 1 of solving this problem here. We're going to solve this improper integral of e to the ax cosine bx dx. This is a specific type of Fourier cosine transform, okay? And all it is, all you need to know, you don't even need to know Fourier transforms. If this is your first time, as long as you know integral calculus, you'll be fine and able to understand this, okay? As long as you're curious and, you know, you're able to think in a strongly, critically anyways. So we're going to be looking at this problem right here, right? So we're going to solve the Fourier transform of root 2 over pi of the improper integral of f(x) cosine bx dx, right? This is a Fourier cosine transform, okay? This guy right here is a cosine Fourier transform that I'm highlighting, okay? So we're going to use that to solve this problem right here. They're connected, okay? And we're going to look at that. So to solve this improper integral, right, ax cosine bx dx, all right, we're going to implement this method. There's multiple methods of solving that improper integral, but one of them is using the Fourier cosine transform. And that's what we were talking about, was this portion here. I showed you a graphical simulation of a Fourier cosine function of a Fourier cosine transform. It's always f of x times some cosine of bx, okay? In this case, f of x was e to the ax, so I just took e to the ax cosine bx and graphed it. But now we're going to find its transform, okay? All right, so let's do that. So the first thing, right, is to know what our f of x is, okay? F of x, what is f of x? Can anyone tell me, please, what f of x is? Anyone tell me what f of x is? Oh, hi, we have somebody. And I help. We're doing something on Fourier transforms. Are you interested? Fourier transforms. That's what we're talking about. Any background in mathematics, integral calculus, linear algebra? Okay, perfect. Yes, nice, excellent. Where are you from exactly? You from the States? Oh, perfect. Oh, India, excellent. Okay, so yes, we're going to be talking about some specific type of how Fourier transforms are connected to to waves and quantum mechanics to some degree. Okay, this is all from my book actually, so it's an interesting book on advanced integration techniques. It's applied mathematics. Okay, all right. So can you see the screen when I'm doing the whiteboard? Okay. Can you see the whiteboard? What I have written on the whiteboard? Just let me know. I may have to stop sharing it temporarily. Okay, let me go back to the desktop. Okay, so when I had it on, it was okay, right? Okay, so yeah, perfect. All right, so yes, we're going to continue with this. Let me know if you have any questions in the process. Okay, so what we're going to look at is we're going to solve this problem right here, okay, using a Fourier transform, Fourier cosine transform technique, okay? All right, so that's this formula right here, okay? And what I just did here, I just replaced f of x with e to the ax cosine bx dx. Let me know if you have any issue with that, please. Okay. Oh, you cannot. Let me try getting back onto the screen here. Just 1 second, share screen. Okay, let me just go to entire screen. I'm going to try doing this. Okay, then I'm going to do this. What about now? Can you see it? Okay, perfect. So when I was on the when I did this and then whiteboard was perfect. Okay. Okay, yeah. So let's get back into look at. So what I was saying here is we're going to solve this problem right here. Okay. This problem right here using Fourier cosine transforms. So a Fourier cosine transform is square root of 2 over pi, improper integral of f of x cosine bx dx. Okay. All right. So all I'm going to do is replace my f of x. My f of x has to be e to the ax cosine bx dx, right? This part here is the f of x. This part here that I've highlighted is f of x, correct? Okay, I think you got that. All right, so that's my f of x. Okay, now I have the improper integral of e to the ax cosine bx dx. Okay, I'm going to go to page 2 now. So this is continuation. I don't want you to see this. I'm going to ask you a question. How would I integrate e to the ax cosine bx dx? How would I integrate this? Just 1 second, get a glass of water. Any thoughts of how to integrate? Chain method. You mean integration by parts, I'm assuming, like uv minus integral vdu. Okay, that's what you meant. Okay, yeah. Let me go back here. Yes, that's correct. Yeah, exactly. Very good. Okay, so you know what you're doing. So here I'm going to let u equal e to the ax. I'm going to let du, this would be straightforward. Du is a differential, so ae to the ax dx. Okay, that's what I'm doing. So I have u and I got my du now. All right, it's pretty straightforward, right? Du is the differential of u. dv now, dv has to be cosine bx dx, right? Right, because this is integral of u dv, right? Integral u dv is uv minus integral v du. Okay, so my dv is cosine bx dx. My v is 1 over b sine bx. Sine integral derivatives. Yeah. Okay. Any question on that? Is that okay? All right. All right, excellent, good. Oh, are we good? Okay. Yeah. Let me know if anything is tripping you for a sec. Sometimes they go fast, so I may make a slight mistake. So just let me know. Okay, good, perfect. All right, so let's go back here. So we already have this. I'm going to substitute into my Fourier cosine integral here. Okay, so the root 2 over pi improper integral eax cosine bx dx. So I'm using integration by parts, the chain method. So root 2 over pi, all in parentheses of 1 over b times e to the ax sine bx. Okay, it's just u times v. We're just following the formula. Okay, minus integral of v du. All right, so integral from 0 to infinity. V, my v was 1 over b. Yeah, 1 over b sine bx. My du is ae to the ax dx. A and b are constants. They're independent of x. They go in front of the integral. So it's just a over b integral 0 to infinity e to the ax sine bx dx, right? Okay. All right, so I assume that is all good. Okay, so we've got that. Next step from here, okay, is to take the square root of 2 over pi, right, parenthesis, times the limit of t approaches infinity. Now, why did I have to do that? Do I need to put a limit there because of this improper integral, or no? Why am I putting a limit? Do I need to put a limit for notation's sake? Why do I need a limit? Okay, crystal clear, good. Yes, but now I have a question. Why did I put a limit here? Right? Why am I putting a limit in front of this entire portion? Okay. Why am I putting it a limit? It is an improper integral. Does it matter if I put a limit? I assume not. Guess what? Oh, yeah, go ahead. Yes. Please think. I'll get back to the board. Sorry. Let me give you time to think. Let me see if you said anything. Yeah, take your time. Take your time. Take your time. Okay, just yeah, take your time. Let's see. Oh, yes, no problem. I'll help you with this, right? So the reason why is because it doesn't matter. I could have kept the infinity, the infinity in my limits of integration, but quite often in mathematical notation, we don't like to have the infinity in our upper and lower bounds. It doesn't matter. I could have kept the infinity there, but I'm just going to replace it as saying limit as t approaches infinity. In other words, we want to just say, to be mathematically precise in terms of writing purposes, that we're approaching infinity and it's not equal to infinity. If I put infinity here, it's not written precisely, right? Because it's like saying that it's equal to infinity, because when we do fundamental theorem of calculus, so subtracting the upper and lower bounds, it's not as accurate writing-wise. Okay, so it doesn't really matter, but it's just better to have it that way, if that makes sense. Okay. Right? So yes, I hope that is making more sense now, right? So now we have this. Okay, so we're thinking, I'm replacing a dummy variable here. I'm calling it t. So I'm saying I'm letting t approach infinity here, right? So limit as t approaches infinity. all in brackets, 1 over b e to the ax sine bx. And I'm going from 0 to t. Okay, I'm going from my lower bound of integration, upper bound of integration is t in this case, replacing it with infinity. All right, then it's minus a over b, integrate from 0 to t e to the ax sine bx dx. I don't want to show you what I'm doing at the bottom. How would I integrate this now? Now I have to integrate this. Let me highlight here, this guy right here, right? Because I wanted to reduce my integral, but now I'm left with another mess. E to the ax sine bx dx. How would I integrate that? Right? You'll notice here that we have an issue with the integral of e to the ax sine bx dx. Any ideas of how to solve it, how to reduce that integral? Let's see. Yeah, so if you mean by substituting, I don't know if you mean by U sub or chain method again. That's what I'm trying to figure out what you mean. Yeah, exactly. Well, not V. I'm going to use a dV, right? So I'm going to let U equal e to the ax dV sine bx dx. I need to use chain method again, right? So what you said earlier is correct, using the chain method in order to solve this integral. But then when I reduced it, I have to chain it again. Okay, I have to use the chain method again. Does that make sense? Substituting. Yes. Well, if you mean substituting in terms of chain method, right? Like the UV, right? UV minus integral of v du. You understand why, right? Okay. I hope that's clear, right? I have to use integration by parts again. The reason why I have to use integration by parts again, okay, is, well, first off, there's no way to integrate e to the ax sine bx dx straight off the pat, right? There's no other way. You have to use integration by parts again, because it becomes cyclical, if that makes sense, right? So I have to be able to do that, right? There's no way around it. Quite often when you're integrating a product of e to the x times cos x or times sine x, whatever it is, you're going to have to do two chain methods, okay? There's no way around it. You have to choose your correct u and your correct dv, okay? So u would be e to the ax, dv is sine bx dx, right? All right. Now, I am choosing u to be equal to e to the ax, okay? So du has to be ae to the ax dx, okay? That's to be straightforward. It's just derivatives. dv is sine bx dx, therefore v, because if I want to get rid of the differential, I have to integrate to get v. So minus 1 over b cosine bx, okay? All right, does that make sense? Okay, good. I just want to make sure you're following. Let me know if something is conceptually tricky, and I'll try to logically break it down. Okay. All right, so we've got that. Now, the next thing is, again, resubstitute into this integral, this guy here, right? So this integral here, we're using that chain method or the integration by parts, you want to call it, in here, okay? So we're going to put that into that integral bracket right there, okay? So we're going to put that information in. So it's going to be the Fourier transform is equal to root 2 over pi, okay? Taking the limit as t approaches infinity of 1 over b e to the ax sine bx. Limits of integration has the lower bound from 0 to t, minus a over b. This integral here, right? I'm just substituting u for e to the ax, okay? You see over here, e to the ax factor. uv is minus b over cosine bx. And then limit of integration was from 0 to t, okay? all right? Then we had, well, remember, we still have, that's my u times v, right? This is my u times v. This is my minus integral v du. The v du part, the v is minus 1 over b cosine bx, right? Cosine bx, that b here. It became positive because it's supposed to be minus integral v du. So minus minus comes positive. So a over b integral 0 to t e to the ax cosine bx dx. Okay, is that making sense to you? Okay, good. Yes, excellent. All right, good. So from here, I'm just saying, by the way, when I'm putting this here, I'm saying IBP again. I'm just saying, I'm just using integration by parts a second time, or the chain method. It doesn't matter what you call it. Yeah, just the product chain method of integration. I'm just using it again. Okay, now from here, it's just algebra. I have to clean up the brackets. You understand? So I'm taking square root 2 over pi, right? Parentheses, the limit as t approaches infinity, okay? Right, all in square brackets, right? The 1 over b e to the ax, right? You can see this here that I'm looking at, okay? E to the ax sine bx, limit of integration 0 to t, minus a over b times negative e to the ax over b cosine bx, limits of integration from 0 to t, plus a over b, integral 0 to t e to the ax cosine bx dx. I'm just cleaning it up now. Okay, then this becomes the square root of 2 over pi, parentheses as the limit as t approaches infinity, 1 over b e to the ax sine bx, limits of integration goes from 0 to t. Then what I want to do is I want to multiply in, correct? Right, I want to start multiplying into the brackets, right? I want to clean it up and then, you know, collect like terms or whatever, right? To simplify the problem, okay? So that's the first thing I'm going to do, okay? So I'm going to do that, multiply in. I'm getting the square root of 2 over pi, okay? Parentheses as a limit as t approaches infinity, okay? Bracket 1 over b e to the ax sine bx. My limit of integration is going from 0 to t, right? Plus a e to the ax, right? This is a negative, this is a negative. It has to be positive, correct? Okay, so a e to the ax over b squared cosine bx. I'm taking the bounds from 0 to t, plus a squared over b squared. This is a squared over b squared because it's a over b times a over b, right? A squared over b squared. Limits of integration from 0 to t e to the ax cosine bx dx. Okay. All right. What you did after solving IBP. What did I do after solving IBP? Okay. Yeah. So what did I do after solving IBP? Yeah. So over here, right? So remember I said I'm using IBP for the second time. So all I'm doing now is I'm just multiplying in, right? I want to multiply the a over b, the minus a over b factor inside, right? So then I can start, you know, simplifying, maybe collecting like terms in the second portion here, if that makes sense. Okay, you know what I mean? Okay, good. Yes. All right. And then from here, we're going to the next step. Okay, the one I sort of raise this part here, so over here, so 0 to t. So now we have limit as t approaches infinity, 1 over b e to the ax sine bx, 0 to t. Okay, plus a e to the ax over b squared cosine bx from 0 to t, minus a squared over b squared. That a squared over b squared is just this here, minus a over b times a over b. Okay, a over b became minus a squared over b squared. And then you integrate from 0 to t of e to the ax cosine bx dx in brackets. Does that make sense? Perfect, good. All right. Then where are we here? Yes. Yeah, so we had the a squared over b squared. We did that part. Now we're on this line over here. Okay, where my arrow's pointing. Okay, so you're not getting lost. So I have my root 2 over pi, limit as t approaches infinity. Okay, I can still write that's fine. Now what I'm doing is I'm putting my limits of integration in because it's the fundamental theorem of calculus. It's a definite integral, so we're going from f of b minus f of a. So 1 over b e to the at sine bt minus minus 1 over b e to the 0, right? Because that x, we're plugging in the x values. Sine of 0, sine 0 is 0, so I don't need to put anything there, right? So it's just 1 over b e to the at sine bt, okay? Over here now, it will be plus ae to the at over b squared cosine bt, right? Upper limit of integration minus the lower limit will be a over b squared. Why is it minus a over b squared, do you think? Why is my lower limit of integration when I plug in 0, a over b squared? Why is it just minus a over b squared? Let me see. Well, so it's just minus a over b squared, right? Right, this part here. So why is it minus a over b squared, do you think? Right? Because my upper limit, I did ae to the at over b squared cosine bt minus a over b squared. Cos 0 is 1, right? My cos 0 is 1, okay? And then e to the 0 is 1, so it's just a over b squared, okay? So minus a over b squared, all right? Any question on that? Let me see if any questions. Yeah, any questions so far? Any questions? Any questions on that a over b squared part? Okay. So let me know if there's any questions. Okay, so no questions so far. So I'm going to continue on. So a over b squared minus a squared over b squared, integral from 0 to t of e to the x cosine bx dx. Okay. All right. Then from here, we can clean this up. This part, this is going if t is approaching infinity, right? Okay, so t should be going to infinity. Now, there should be something here, okay? Should be something here. There should be something here. As my t goes to infinity, right? This portion is going to be eliminated. This is approaching 0, right? So this portion here that I'm talking about has to approach 0, right? Has to approach 0. You understand? Right? This here has to approach 0. Okay? And the reason for that is because if you look at, this has to go to 0. Let me see over here, 0. This approaches 0. Okay, these two portions have to approach 0 because if you were to look at a graph of e to the negative x, right? Right? So let's see here. So if I drew a graph, right, of e to the negative x is decreasing, sorry for that. Let me make a good graph here. So let's say you have on the side. By the way, my approach is always to draw diagrams and graphs because that helps. If you're not able to algebraically or use a mathematical method for graphing that you don't know about, just draw the regular function to see the behavior of the graph, and the behavior of the graph will tell you what is happening to the equation. Okay, so if you look at this guy here, okay, let's go here just 1 second. So this is y equals e to the negative t. As t approaches infinity, then e to the negative t has to approach 0. Correct? Does that make sense? All right. That's what oh no, I'm sorry to hear that. Is your internet better now? Okay, good. All right. All I was saying is this portion here. Sorry about that. Just give me a moment. I was just. By the way, I'm going to show you a graph after. That will be interesting. That sort of gives you like a geometric description of what I'm talking about too. This portion over here. Let me just rewind. I was talking about taking t approaches infinity, okay, of e to the negative at. This is supposed to be negative, by the way. Right? This is supposed to be negative. Yeah. So I made a slight mistake. These are supposed to be negative t at's, okay? But don't worry, the algebra will still come out fine. I forgot to put negative because the original question was to find integral of e to the negative at cosine bx, right? Whatever. Okay. So there's supposed to be a negative there. Okay. So what I was saying is that my question is, if I take the limit as t approaches infinity, what happens to this guy here? Right. So if t approaches infinity, what will happen to e to the negative at? Yes, it has to go to 0, but why is it 0? Why 0? If you can tell me. Yes, why? What makes you say that it's 0? Well, there's a reason why it's 0. Yeah, exactly. Yeah, that's exactly it, right? 1 over infinity is 0, right? And or you can also, well, everyone should know that, right? But another way to do it is you can always plot a function y equals e to the negative t. It's a decreasing function, right? It's exponential decay. You can see as t is approaching infinity, right? As it approaches infinity in this direction, right? E to the negative t is approaching 0 because it's asymptotic to the t-axis, right? Okay. Right. All this stuff is in my book, by the way. If you're interested in learning calculus at an advanced level and getting ahead, this book is for you. Are you interested in maybe reading more on this topic? This is from my book, actually. Yeah, it's from my book. Yes, yeah. Right. So this is. Let me show you here. This is the cover of my book, right? Advanced Integration Techniques. Okay, so Mastering Advanced Integrals and Applications, perfect for university students. Okay. Yep, sorry about that. Let me go over here. Yes, of course. You can find it at, yes. Yeah, you can find it. Let me give you the link. The STEM1online.com/books. You can look at it after, right? Because we're going through the problem solving. Oh, thank you. I appreciate it. Yeah, yes. Yeah, so yeah, it will be really handy. It will be really handy for university. Yeah. Yeah. It has practically everything. There's an ebook. The ebook is like, if you like ebooks, you can have it anywhere on your phone, on your iPad, doesn't matter. It's just going to be really handy. Especially if you're in school or whatever, you just go through it and yeah. And if you want extra practice on the side, it's very good. Okay. All right. Okay, so let me get back here. All right. So, yep. All right, so we were talking about as t approaches infinity, then e to the negative t is going to 0. Okay, so this is going to 0. Also, this has to go to 0, right? This goes to 0, this goes to 0. I'm just left with minus a over b squared minus a squared over b squared, integral of 0 to t of e to the ax cosine bx dx, right? All right, cool, excellent. I'll give you the details after the live show on how you can get the book. I gave you the link, but you may need some other information. So yeah, I'll give you after the live show. All right. Okay, so let's get back to it. So I was just going to limit as t approaches infinity. That's disappearing. That's disappearing. I'm just left with the minus a over b squared minus a squared over b squared integral, improper integral of e to the ax cosine bx dx. Okay. And what ends up happening is something very interesting. Okay. Something very interesting. Something interesting happens here. Okay. You'll notice that we cycle back to this e to the ax cosine bx dx. Okay. All right. So it's pretty interesting that we have that. So, okay, we have that problem. And I can, again, reduce, as you can see, by collecting like terms, multiplying into the brackets, I'm able to reduce my integral more and more, right? However, though, once I've done this and I get to this line over here, I now have an issue. I need to be able to integrate what I started with. How can I do that, do you think? Yeah, no problem. Yes. Yeah. Okay. So you can always stay in touch. Also, if you have any questions, right? It's oneonline.com. Okay, for questions, or any questions, any questions. Okay. All right. So for any questions, you can reach me there, whether it's for tutoring or whether it's for my book. The link will be there. Perfect. Okay. Thank you, Anrag. We'll keep in touch, and hope you buy my book soon. All right. Have a good day, and take care. All right. All right, so we're going to get back to the board, right? So we want to integrate the improper integral of e to the ax cosine bx dx. Now this is a bit of a paradox because what we were trying to solve was the product of e to the ax cos bx. Okay, the problem is we don't know how to integrate that, but there is a trick that we can do. Okay. Right? There's an interesting trick that we can do here, right? I just need to rearrange. I just have to rearrange this integral on the other side. Okay, so I move my integral. I'm going to move my integral over here, the left-hand side, right? Because initially what we were integrating was the improper integral of e to the ax cosine bx dx, okay? And it's equal to all of this. So if I move this guy over here, I'm collecting the like terms of the integral, okay? If I move like terms on the left-hand side, I will isolate for this improper integral that I don't know how to solve. And then I'll be able to get my result. Okay, so now I get improper integral of e to the ax cos bx dx plus root 2 over pi a squared over b squared improper integral e to the ax cosine bx dx, right? All right, and what ends up happening, I'm not going to go through all of it. It ends up being this result. Okay, this is the result that we should be getting at the end of the day of e to the ax cosine bx dx. This would be a all over a squared plus b squared. Okay. That is the result that we should be getting. All right. So that is how we improper integrate this problem. Okay. Any questions? Let me know if there's any questions on the problem. Okay. Yeah, this is a perfect problem for when it comes to the subject. That's why I have it in my book in the first place. Pretty much, I felt that this would be appropriate for very advanced high school and undergraduate students. Okay, like this is the best problem you could do on integration by parts because it practices rigorously how to do integration by parts. Okay, it requires quite a bit of creative thinking. Okay. Now there's another way we can solve this. Ooh, interesting. Another way to solve this problem. Oh, hi. It's good. Okay. Yeah. Yes, we have a new person. Xylixin. I can't pronounce names. It's a math problem. We're not good verbally. Well, I'm very good at explaining mathematical topics, but pronunciations is the problem. Is it Xylixin? Xylixin? I can't pronounce. I hope you have an interest in mathematics or you're some sort of student. Any background in calculus or linear algebra. That's what we're doing here. Yeah. Yes. When it comes to pronouncing things, sometimes it's a bit of a problem. Yep. Well, I do my best. So any background in calculus and linear algebra or either of the two? Oh, no problem. No problem. Okay. But it seems that you have an interest in learning. Can you tell me a bit more about your education, what your interests are in mathematics exactly? And then I can maybe sort of make it relate to what you're doing. Because yes, this is advanced, but I can make it relate algebraically. And integration is just it's a type of calculus, right? Okay, I see. Let me explain in layman terms. You'll understand this. You know about areas, okay? So areas, when you find the area of something, right, you use geometry to find the area. Let's say the length, width, height, whatever, right? Well, length with height would be volume. Well, length times width for a rectangle, okay? Integration is a way to calculate areas of curved shapes. So any type of curved shape, we're going to use integrals, okay? So if I wanted to calculate the area of, let's say, a shear block of some sort or a shear curve. Yes, that's like trigonometry for circles. Sort of, not quite. Let me give you an example. Let's get to the whiteboard here. You can see my whiteboard, right? Let me know if you can see it. Okay, yes. Okay, I'll just on it. So I'm going to highlight here this graph. Okay, X, Y. And you know about graphs, I'm supposing. And let's say I have a curve. Let's say some sort of parabolic curve. Okay, like this. All right. And let's say this parabolic curve starts at the origin 0, 0. Okay. And I'm going to some coordinate 1 here. Let's say 1, 0. Okay. I'm going to highlight this. Okay. I want to find the area under the right arc of this parabolic curve, for instance, from 0 to 1. Okay. So that's this shaded area here. You see what I mean? You understand? That's an example of integration, finding the areas under any type of weird type of curved shape. Okay, maybe something like this. Okay, maybe I have something like this. Let me give you an example. Okay, so maybe a curve like this. Okay, let's say I want to find the area from negative, let's say from the coordinate, let's say -2 here. Okay, and let's say this is 0. Okay, and obviously if I'm going from -2 to 0, I'm looking at this area here. Okay, does that make sense? Yes, but not specifically a parabola. Any type of curved surface. Okay, any type of curved surface. You understand? Okay, right? Any type of curved surface. It can be used, now to answer your earlier question, it can be used for triangles too. Okay, it can be used for triangles to find areas under triangles too. It just adds to the geometry, right? So any type of shape, but including curved shapes, because regular geometry can't deal with very curved and abnormal shapes. Here it can. Okay. All right. Give me one moment. I have to use the washroom. I'll be right back. Sorry about that. Be right back. 1 second. Okay, I'm back. Sorry about that. Yes, I appreciate it. Okay, so yeah, let's get back to it. Okay. So I can give you an example specifically to prove that it works for triangles. Okay, if you want to find areas of triangles. Okay, so let's say, for instance, I'm going to go over here, right? Okay, so let's say you have a graph here. Okay, this is x, this is y. Let's say I'm at a coordinate of 0, 0, 0, 0. Right, I start at 0, 0, and I extend to, let's say, 1, 2. Okay. And let's say over here is maybe 3, for instance. Doesn't matter. Okay. And I draw a triangle like this. Okay, right angle triangle. I'm going to compare the two methods. Normally by using area equals base times height divided by 2. Okay. And then I'm going to use integration so that should give us approximately the same thing. All right. You know what I mean? All right. So if you look at this coordinate plane here, I have the triangle at 0, 0 and a 1, 2. So normally using regular geometry, you use method 1. Method 1. Okay. Method 1 is area is equal to 1/2 base times height. Okay. Okay. So then here, this is going to be 1/2 the base. Now the base is from here to here, right? On the x-axis. Right? The base would be what? What's the length of the base here? What do you think the length of the base is? Right? Look carefully in the diagram. We're at 0, 0 and 1, 2. The base is the x-axis, the length of the x-axis. Yes, yeah, exactly. 1. Right? So 1. And it looks like my height should be, let me see here. There's one. Oh, 1 second here. Made a slight mistake. That coordinate was wrong. Sorry about that. This would be a 2, 0. Sorry, my mistake. Yeah, because they're still on the x-axis, right? 2, 0. X is 2, y is 0. Yep, sorry about that. Yeah, AJ, just give me a moment. Just trying to help Modgers here. Converging the physics of Fourier transform. Yeah, we're going to talk about that later. Yeah, we're going to talk about converging the physics of Fourier transforms in quantum mechanics at some point. I'm just helping Modgers. Modgers here. What it is? Okay, Modgers and Xylickson. So with their questions, but we'll do quantum mechanics, the intersection of quantum mechanics later. Yeah. Okay, so let's get, let me get back to it. I was talking about, yeah, so here would be 1, base would be 1, height would be 3, right? This is regular triangles, right? So this would be 3 over 2, right? Area 3 over 2 units squared, right? I'm just explaining to a grade 10 student right now what integration is. So sorry about that, guys. I'll get back to this more serious stuff in a moment. Okay. Answer your questions. All right, so then after method two for Xylickson and Modgers, right? How this compares, you would just take area equals integral, right? From 0 to 2, f of x dx, okay? Right, base times height divided by, so we're going to compare base times height divided by 2 here, okay? Now, this is just a function, right? Like y equals x, okay? Correct? This would be y equals x, all right? So this is just going to be integral from 0 to 2 of x dx, okay? Right? Of some sort. And then taking the area of that to give us the exact value, okay? Does that make sense, Xylickson? Sorry, I have to sort of rush. I have some guys here that have questions. Okay. All right. I hope that makes sense, right? My point is, at the end of the day, that this should come out, right? This should come out like this, okay? That after doing the area integral should be some scalar factor of 1/2 x squared, right? And this in reality is the same thing as saying area is 1/2 base times height for a triangle, right? I hope that put it to layman's terms for a grade 10, 11 student for integration, okay? All right, now when it comes to you other guys, right? I was initially looking at integrating e to the ax cosine bx. I was going through all this jazz with some other guys earlier, okay? Taking the integral of e to the x cosine bx dx, using a Fourier cosine transform, and then after doing all of this integration by parts and everything like that, I reduced down to a over a squared plus b squared is the result of this improper integral. It's from my book, Advanced Integration Techniques. If you want to refer to that, if you want to know more about it, there'll be more information in the description, or you can look at my channel. If I forget to put it in the description, I shouldn't forget to put it in the description. Okay. All right. Does that make sense? Oh, yes, yes. Well, you don't know who comes into the live channel. Right? Maybe I should say 18 plus. No, I shouldn't say that. 18 plus mathematically, anyways. Anyways, or 17 plus. Yes. Yeah. Otherwise, it would be it would be challenging. But I'm glad Xylickson has an interest in this in the first place. It shows mathematical maturity. It's not easy to be, to comprehensively understand this, right? But thanks, Modgers. I'll go back to Xylickson pretty quickly because, yeah, I appreciate it. Yep. Thanks. I don't want to rush. But anyways, Xylickson, what I was talking about earlier, where was I again? This was page 2. Page Yeah, page 3. So that's what I was mentioning, right? We can find areas of triangles, right? As I said, using method 1, using basic geometry, 1/2 base times height, and you get the area. The other way is to do integration. What you do is by taking the integral from A to B. Actually, I should write a formula for this, so that's where you understand what I'm talking about. There's a formalization of this, right? So that's why you know where I'm getting this 0 to 2. So integral from A to B of f of x dx. Okay, where A and B are the x coordinates, right? The upper x coordinates 2, lower x coordinate is 0, right? So what you would do is you would say area equals the integral from 0 to 2, okay? F of x, we need to define what f of x is. I didn't say what f of x is. I just said we had this triangle, right? How do you think we can find this function f of x that I drew here? How can I get the function f of x, the equation of, it's an equation of a line, actually. Right? Alex, how would we get it? Slope formula, y equals mx plus b, right? I know what, I can get my m really fast. Just want to go back to this, Alex. Sorry, guys. Yep, so just go over here. Just 1 second. Just give me a moment. Okay. All right, so we were looking at this guy here, f of x, the slope here, right? You would just do slope equals y2 minus y1 over x2 minus x1, right? Right, in this case, to get the slope of the line, of this line here, and it's just y2 minus y1. So y2, right? So y2 minus y1, x2 over x1, and that will give you the slope of f of x, and then you get the area from integrating, and this should come down to 1/2 x squared. Okay. All right. So let's get back over here. So for you other guys, Moggers and everybody else, as I said, I was using Fourier transforms to integrate e to the ax cosine bx dx. Okay, and the way to do that is just to use integration by parts twice. That's what I did here. Okay, I use integration by parts twice, and the way to do that, I was able to mathematically go down through it and get actually my results. Yes, Moggers. Moggers is yes. Yep. I see Moggers is also likes to go back to grade 10. I don't. I'm advanced. That's why I'm doing this. It's funny when you have kids coming in. Yeah. Anyways, back to what I was talking about to answer Moggers thing. With the Fourier transform and stuff like that connected to quantum mechanics. We're getting there. Let me just explain what I was doing with the Fourier transform. I was integrating e to the ax cosine bx dx. The way you would do that, I took a Fourier cosine relationship here. Well, actually, it is a Fourier cosine of some sort. I did, what's it called? Integration by parts, because this is a product formula, right? E dx du would be ae to the ax dv cosine bx v 1 over b sine bx. Plugged it into the Fourier cosine formula. In reality, I noticed there was a slight mistake here. I sort of made the lower limit of integration minus infinity to infinity, because initially a Fourier transform is from minus infinity to infinity, if that makes sense. Okay, right? So I sort of forgot that. All right, so I just want to make sure that you're following along. So minus infinity to infinity. Okay, all right. Yes, Moggers agrees. Yes, sir. Yes. Yeah, I just noticed that right now. That might have altered some part of the calculation. I have a million equations in my head, and I can't keep track of all of them. Anyways, back to this is all from my book, by the way, because I'm an author. I've written some math books, academic math books. Anyways, back to it. So I was looking at taking the limit of integration from minus infinity to infinity. So again, when we do this, obviously I'd have to use integration by parts again on that e to the ax cosine bx dx, right? Because of the fact that it's a product again, right? Right. So I'd have to use it. I use it once, right? So the first time I get this, okay, this e to the ax sine bx dx, right? Because uv minus integral v du, okay. I'm going to explain why I get to the second second time I'm doing integration by parts again, is because the limit as t approaches infinity. This is an improper integral, so I might as well see t approaches infinity. Now, the fact that I just realized that I forgot to put my minus infinity at the bottom will alter the result at the end. I hate when that happens. But sometimes that happens, especially when you're doing when your equation is long, right? So anyways, my point is we should be having bounds from t 0 to t. I'm putting a dummy variable here because we're going from integrating from improper integrals. So usually we put limit as t approaches something. Okay, so that's why I'm doing this. So I'm just saying 1 over b e to the x sine bx, 0 to t, integral 0 to t ax sine bx dx. Going through all this is, again, integration by parts, right? The second time, because it's e to the x sine bx dx, it's cyclical. You get all of this, okay? All of this jazz. And what we should be getting is a over a squared plus b squared, right? I forgot to put here this minus infinity, right? That's why I didn't continue. I sort of jumped from here to here. That was a mistake. And the mistake was because there's a minus infinity, right? Because when you have an improper integral from minus infinity to infinity, you should be adding two integrals. You should be taking minus infinity to 0 plus integral from 0 to infinity. As you can see here, I did not put that into my brackets because I only integrated from 0 to infinity. That was my mistake. Okay. Yeah, exactly. Yeah, exactly right. Yep, that's right. Oh, by the way, I want to mention, don't forget to like and subscribe. I really appreciate it if you can like and subscribe, and it will be handy for any of you guys there. But yeah, that's exactly it. Integration by parts, right? Want to be able to, and then do back substitution again and again, cyclical, and then rearrange, right? So what I mean by rearrange, okay, I'm going all the way here, right? The point is to eventually rearrange this guy, right? Because we get back, if we do integration by parts the second time, e to the x cosine bx dx, rearrange, isolate for integral 0 to infinity of e to the x cosine bx dx, right? And then after doing that, we should get down to this. As again, the reason why I have this nonsense right here is because I was only integrating from 0 to infinity for my Fourier cosine. It's supposed to be from minus infinity to infinity, so I sort of added another integral for any of you guys who are saying what is going on. Okay. All right. Okay. All right, let's go back. So I solved that. Just to let you guys know, there is another interesting way to solve this, method 2. Does anybody know how to solve this using a second method of just integrating 0 to infinity e to the x cosine bx dx? How can I solve this using a method number 2? Ghost Gaming. Hello, Ghost. Hi, Ghost. Welcome to my mathematical channel. My mathematical channel. Yes, I'm going to answer your question, Mongers. I'm going to say pretty much the way to do this, right, is we're going to use complex numbers. Leibniz, you mean using Leibniz rule with Feynman trick? We could do that, but it would be easier, I think, to use. You understand what I mean? Complex numbers. Yes, Gauss Gaming. I see that. Yes, I see you have interest in calculus. We're doing that right now. Hope you have some elementary integration. That would be handy. But yes, Moggers, we're going to do elementary complex numbers, right? Complex numbers. So what I mean by that is let cosine x equal to e to the ix plus e to the negative ix all over 2. You understand what I mean? Okay, right? You should have seen this identity before, that cosine x is just the exponential cosine complex exponential. Sorry. So cosine is equal to the complex exponentials, right? E to the ix plus e to the negative ix all over 2, right? Okay, you understand what I mean. Perfect. Just want to make sure everyone else is understanding. Okay, I don't want to. I know you guys may all be at different levels, but I just want to make sure everyone else is understanding. Okay. All right. So we've got that. Now, what I'm going to do is I'm going to put bx here, a b. And if I put b, it's going to become e to the ibx plus e to the negative ibx all over 2. Okay. Right. That makes sense because we're dealing with cosine of ibx, cosine of bx, sorry, cosine of bx here that I'm highlighting, right? I'm dealing with cosine bx. So I want to figure out what the complex exponentials are in terms of bx. Next, I will substitute that into my cosine of bx. Okay, so when I do that, I'm going to get my improper integral to be e to the ax times parentheses e to the ibx plus e to the negative ibx all over 2 with respect to x. Any question? Yeah. Yes, Smoggers. Excellent. Yeah, that's what I meant. Euler's formula. Yeah, exactly. Gauss gaming, I subbed. But I got to move on to Cam, so have fun. Yes, Gauss game. But before you go, like and subscribe. Please like and subscribe. It'll be really handy. And if you have any questions on elementary calculus, I can always help. All right, Moggers. Yes, we're going to get back to it. Let me see here. So we're looking at this guy here. Then from here, I'm just moving the 1/2 of the front. Why I did that, it's a constant. It makes it easier. It makes my life easier. Now I have e to the ax, all in parentheses, e to the ibx plus e to the negative ibx dx. Now it's just, basic forms of integration, okay? This now becomes 1/2 integral 0 to infinity. I'm taking the integral operator inside of the parentheses. E to the ax times e to the ibx dx plus 1/2 e to the ax times e to the negative ibx dx. Okay. From this step on, I go to 1/2 improper integral of e to the whole power of a plus ib parentheses x. I can add the exponents because I'm multiplying by their common basis with respect to x, plus 1/2 improper integral of e to the power of a minus ib, where a minus ib is a complex number, times x dx. As you said, all I'm doing is Euler's formula. Make sense? I assume so. Yep. All right. I assume you're following, Moggers. Everybody else, just hang in there. I want to answer other people's questions. Don't worry, we're going to get to some applications to quantum mechanics. Okay, we're going to talk about that a little bit. Okay, so we have, we're going to do, the way to integrate this is use substitution, right? This is just a regular integral of e to the x. In this case, e to the x being, a plus ibx, right? So I'd have to use a u substitution, right? Everyone follow? Yeah, exactly. Okay, Moggers is getting it. Okay, so u equals a plus ib. Therefore, du has to be a plus ib dx, right? And then dx, my dx is just going to be du divided by a plus or minus ib. I put plus or minus because we're dealing with both this guy here and this guy here in the complex exponential part. Okay. All right. Then from here, it's just going to be 1 all over 2 a plus ib, improper integral of e to the u du. I'm doing u substitution, replace all x's with the u's, appropriate u's. And since my dx was du over a plus ib, I just put the a plus ib in front right over here because it's a constant, right? Same thing here, 1 over 2 times a minus ib, improper integral of e to the u du. Okay. All right. And then from here now, all I'm doing, I'm taking the limit as t approaches infinity. T is my dummy variable. Reason for that is because quite often, most of you know that we don't like to have infinities in our upper bounds when we actually do the definite integral. So I just put the limit there. Most of us know that. So this 1 over 2a plus ib, blah, blah, blah. You already know what this is. Continuing from this step over here. Then I go down here. You can see that my limits, and now I'm just putting the limits of integration in. Okay, so 1 over 2a plus ib, e to the a plus ib, because u is a plus ib, 0 to t, 1 over 2a minus ib, e to the a minus ib x from 0 to t. Okay. Now, I want to input my upper and lower limits of integration, plug in the t here, plug in 0, f of b, this is my f of b minus f of a, f of b minus f of a, and the next one is going to also be f of b minus f of a, right? So you can see here the algebra is pretty straightforward, right? All right, so I get that, my t's and zeros into my respective parts. Now, this portion here is approaching 0. Oh, okay, perfect. I can move on. All right, yes. And what you will get eventually down is that you get all of this after the algebra, a all over a squared plus b squared. And we've proven it. So there's multiple methods to do this, okay? All right, so yes, I'm going to move on. I'm going to move on to some other interesting stuff. So as I mentioned in my live show today, it's the Fourier transform clinic, I like to call it. Or in other words, Fourier transform clinic, where we connect the Fourier transform to its applications with, waves and quantum mechanics, some applications of quantum mechanics. It's all in my book. It's an applied mathematics book, right? Advanced integration techniques, where we master advanced integrals and applications. Okay, you can find it at STEM1online.com. I'll also put that there in my link for those of you who want to look at it. So let me go back to the desktop. So for more, if you like learning more about the connections of this type of high-level calculus and its applications to physics or stochastics or statistics, you can check here, right? So STEM, so just 1 second, www.STEM1online.com/books for more info on this topic. Okay. All right, so if you want a resource, you can always check out my book. All right, so let's get back to it. So in today's video, we're just going through some problems and concepts from my book. We looked at the visual intuition of the Fourier transform, how real and complex exponentials combine to form solutions, Gaussian transforms. That's what I want to talk about. We haven't talked about that yet, Gaussian transforms. Okay. I'm showing you guys too much. So part 2 is to solve this improper integral from minus infinity to infinity of e to the negative I omega x times e to the negative x squared dx. Okay. So we're going to be looking at integrating that. That's another problem from my book in this section, right? Is looking at the second problem, the integral from minus infinity to infinity e to negative I omega x times e to the negative x squared dx. Anyone have any ideas of how to solve this integral? Actually, I already set it up. It's a regular Fourier transform. You can say it's a Fourier transform automatically, but mathematically, how should I proceed? This is why I carry a cup of water. I'm giving lectures. It's this right up my throat. Anyone have ideas how to do this? The gamma function. Okay, not quite. It's not the gamma function particularly. Okay, let me explain. Okay, let me explain why it's not the gamma function. Just give me a moment. Okay. Ah, damn it! I hate when that happens. Sorry about that, guys. Let me just go over here. All right. So this guy right here is not the gamma function. The gamma function, first off, let me put on the side here what the gamma function is. Gamma of, let's say, n, okay, doesn't matter what I call it, little n, is equal to the integral from 0 to infinity of x to the power of n minus 1 e to the negative x dx. Okay, this is not a gamma function. This is not in the same form of a gamma function. Okay, a gamma function is calculating the improper integral from 0 to infinity of a product of some variable x to an exponent times e to the negative x dx. And it also calculates interesting factorials, maybe like 1 factorial, 2 factorial, even 1/2 factorial, fractional factorials. All positive factorials excluding negative factorials. Negative factorials would produce nonsense. Okay, does that make sense? Right? Well, you could say you're closer. In reality, well, let me go back here, right? So it's neither gamma, not quite the Laplace. Laplace, right? Laplace transform. It's in my book, and it clarifies the distinction, right? The Laplace transform is this: Laplace of f of t. I should say f of t to be precise. F of t is equal to integral from 0 to infinity of f of t times e to the negative st dt. Okay. I mean, you could say that there is a relationship here. I mean, your e to the negative st would be maybe your e to the negative I omega x, you can say, but not quite. There's a complex number in front. It's not quite a Laplace transform, right? It's still a Fourier transform, right? Let me show you the difference between Laplace and Fourier, right? A Fourier transform, right? Fourier transform of f of t, right? Fourier transform is just saying the integral from minus infinity to infinity f of t times e to the I omega t dt. And what this is measuring, it's going from t space, right? So Fourier transform goes from t space base to omega space. Okay, so I go from t space to omega space. Okay, for a Fourier transform. Does that make sense? Okay, so it's not quite a Laplace transform. Does that make sense, Mongers? Okay, assuming that it's making sense. All right, so let's get back to it. Okay, let's get back to it. So we were at going from, we want to calculate this. Now to calculate this integral, okay, all we're going to do for the solution is the following, right? I'm going to take the product of this integral, okay, so minus infinity to infinity, e to the negative I omega x times e to the negative x squared. And what I can do is I can add them. I can add what their exponents have, right? It's just a product, right? Just basic exponent laws. Two base products, same bases, and then multiplied, you add their exponents. So negative x squared plus I omega x. And I put a negative outside, okay? Now, the way to integrate that, this is a standard form of a quadratic equation, right? Yeah, it is an eigenfunction. You want to know how to solve it. Yeah, I'm assuming you got stuck over here. E to the negative of x squared plus I omega x. It looks weird. Okay. I'm assuming that's where you're having the issue. Right? The way to solve it is just pretty much doing this, right? So you have e to the negative. So see here, right? I have it like this now, okay? This is a standard form of a quadratic equation. I have ax squared plus bx plus c, right? In my exponent, right? It's a quadratic equation. I can complete the square on it, correct? And simplify this nightmare, if that makes sense. Okay, yes, you're already understanding. I hope my methods are handy for you guys. Okay, so completing the square, b over 2 all squared. B, in this case, is the positive I omega. Okay, I omega divided by 2 all squared. Okay. All right, so this would be I omega all over 2. All right. I don't think there was a need for that negative there. How did I get my, is it always, I always forget. Is it minus b over 2 all squared? What's b over 2 all squared? I always forget. Doesn't matter. After the square, we'll cancel the negative anyways. But it should be, yeah, the b over 2 all squared anyways. All right, so I omega over 2 all squared. This becomes I squared omega squared over 4. I squared, you already know, is a complex number, -1, negative omega squared over 4. Okay? All right, now from here, we use some interesting approaches here. So it requires some creativity to solve that problem. Right? This problem is not as straightforward when it comes to integration. But as you can see, my limits of integration from minus infinity to infinity, right, of e to the negative parentheses. I just substitute back in my plus or minus b over 2 squared, right, at the end here, right? If you remember with completing the square, plus or minus b over 2 squared gets added into the brackets, correct? Okay, so what we have now is we're going to have the integral from minus infinity to infinity of e to the negative parentheses x squared plus I omega x, right, plus omega squared divided by 4 minus omega squared over 4, okay? All right. Now, this plus omega squared over 4 comes from multiplying that negative factor outside. If you remember from completing the square, you always take whatever is in front, your factor in front of the parentheses, multiply by one of these guys over here. This becomes omega squared over 4. Okay? All right, so I hope that is making sense for those of you who are, yes, are for factoring. Our intentions to make a whole square. Yeah. I'm trying to get it into a perfect square, if that makes sense. If you know what I mean, like a perfect square trinomial of some sort, like a plus b all squared. If you know what I mean, you should know what I mean. Otherwise, you wouldn't be able to understand this stuff. Yeah. Okay. So yes. All right. So we're going here. So we're taking. So what I had here was e to the negative. Now this became x plus I omega all over 2 squared, right? Because you can see that this is just a squared, right? A squared. I'm putting in the form a squared plus 2ab, ab plus b squared from the exponential earlier, right? Okay, so I have that. All right, so then from here, I compressed it into a plus b all squared, right? Multiplying this out, this by this, I get the positive omega squared over 4. Okay, from there. Then improper integral from minus infinity to infinity, e to the negative x plus I omega all over 2 all squared times e to the omega squared over 4. Why did I do that? I mean, did I need to do that? But why did I just break them up into their individual product factors, e to the negative x plus I omega over 2 squared times e to the omega squared over 4? Why did I do that? How did I get to this? Why did I want some input here, guys? See if anyone is thinking. Anybody thinking? Maybe use logarithm. No logarithms. No. We don't need to do that. That would involve inverting this entire function. We don't need to do that. We just go step by step with what we have, right? From step A. Sorry. I'm going to explain, how the whole square is helping. The reason why we want to go from a standard, the standard form of a quadratic that we had here, ax squared plus bx plus c, into a plus b all squared, is because this guy over here, as a perfect square, will represent a Gaussian integral, minus infinity to infinity of e to the negative u squared, where u will be x plus I omega all over 2 squared, right? Du is equal to root pi. You should know what a Gaussian integral is. Right? Gauss. It's just Gauss. Okay. Is that making sense? I want to compress it from standard for. You see how? So you can see here. I hope this is helping. Quite often, the problems that I discuss and the problems from my book are all require you to use multiple different areas of calculus or linear algebra and stuff like that, right? To make connections, because I think that my approach is always, as long as people are able to strengthen their critical thinking with the hard problems, that's the way I've done things. Okay, so this is a classic example, right? So we have that. So we have times e to the omega squared over 4, right? And then what I want to do is I want to factor out these e to the omega squared over 4, right? So then this is the improper integral of e to the negative x plus I omega all over 2 all squared dx. Okay. Now the e to the omega squared over 4 is a constant because it's not dependent on x, right? Nothing's dependent on x here. Only this is. Okay. Now, as I mentioned, right, I'm going down over here. As I mentioned, it's a Gaussian integral. Okay. Where I'm going to use u substitution, like u equal to x plus I omega over 2. du is going to be the differential of dx, because if I differentiate this, this becomes dx. I will substitute into this guy over here, okay, back into my integral, substitute back into this integral here. This integral, right, this integral is just e to the negative u, right, because I said that was my u, right? So this is just root pi, okay, because you should know that the integral from minus infinity to infinity of e to the negative u squared is root pi, okay? All right, and then from there, right, we're going to get root pi times e to the omega squared over 4. Somehow I'm being sloppy. There should be a negative. Yeah, it's supposed to be a negative here. Somewhere in my calculations. It's a negative. It's supposed to be negative. I hate when the little things trip me up. Always the smallest things trip me up. Like I forget to put them. Yeah, you have to pay attention. Yeah, it's probably because of what I did here for the factor multiplying out, but that's okay. You get the idea. Okay, and that's how we get this result of this particular integral. Okay, so this integral here, we just solved it. Okay, any questions on that result? Yeah, exactly, by definition, pretty much. All right, so let's move on to the next thing. Let's get back to our checklist of what we're doing. So we did, yeah, so we did 1, 2, and 3 research level problem solving. We're going to talk about what that is. What I mean by that is connecting it. I don't know if it's the research level problem solving. It practically is research, this level of mathematics. But I'm going to talk about the relationship to quantum mechanics, how Fourier transforms connect to quantum mechanics. So just give me a moment. Okay. So first off, let me get back here for a sec. Back to the desktop. Just give me a moment. I'm glad you're liking this, mockers. Okay. Hope you'll like and subscribe. All right, so let me continue here. Okay, just give me a moment. I want to figure out how I can go on. Yeah, that's what we're going to do. Yeah, I'm going to go to the whiteboard. Yeah. All right, so let's go to the whiteboard. Okay, so I may need to take another page here because it's taking quite a bit. Okay, I'm going to talk about the relationships of quantum mechanics if I can. So applications. Applications to quantum mechanics, quantum QM. Okay. Just give me a moment. Okay, I had some stuff I wanted to point out. Just give me a sec. Oh, thank you so much. All right. And I hope you will be looking into my book. My book has a lot of interesting stuff when it comes to advanced calculus and its applications in stochastics and quantum mechanics. If you can check that out. Yep. All right, so I wanted to talk about specifically introduction to position versus momentum, or maybe I should get into it more. I'm trying to think if I should go through it. Like there's a lot of stuff. I don't know if I have time to do that, or if I should just put up my Word doc and just sum up the points that are important, the integrals, the language that's used. I don't know how many of you are just pure mathematicians and how many of you are just physicists, but for those of you who are just pure math, you may need to know some of the nomenclature that I'm talking about here. Just give me a moment. Let me see if I can pull this up. If I can make this. Yeah, I might share the screen like this. Just give me a sec. Okay, just 1 second, guys. Just 1 second. give me a second. I'm going to share screen. Share screen again. I see what you mean. Let's see, entire screen. Okay, so entire screen, share. No problem, August. That's fine too. Yeah, that's what I'm trying to decide for the audience. But that can take a long time. I'm trying to see how I can sum it up to the important parts. Okay, I think I have an idea. I'm just going to remind myself some stuff here. Just one moment. Because I'm trying to see, I have a Word doc and go through the important points and stuff like that. Just give me a moment. Yes, one sec. Okay, one sec. Yeah, I think we're going to talk about this. Just give me one moment, guys. Yeah, we'll talk about that. And we'll talk about this. Okay. Yeah, I think we're going to talk about this. Just 1 second. Yeah, we're going to talk about position and momentum first, starting from the basics of nomenclature. Okay, so let's do that. Okay, I'm going to go back to share screen. Yeah, share screen. Yeah. All right, so applications of quantum mechanics, starting off with position versus momentum. Okay, so position versus momentum versus momentum. Okay, and I'm going to do that with the following. Yes, so I have some notes that I had down. It's quite a bit of stuff. I'm just going to get to the important things. Okay, so in quantum mechanics, right? So in quantum mechanics, all right? Every particle is a wave function, obviously, is a wave function. Okay, so what I mean by that is you can have something like this. Let psi of x be a wave function. So psi as a function of x will be a wave function. So psi of x, and x being the position. And quite often you can have curves like this. I want to make it better. Sorry about that. You can have all sorts of wave packets. I'm going to put a family of curves for you. What I mean by wave functions, you have periodic functions. You can have any type of something like this, okay? Or you can have something like this, right? Let me see here. Maybe something like this, right? Any type of family of wave functions. This is a family of wave functions. Okay. All right, so we have family of wave functions. Now, at the same time, a wave function psi of x, okay? That's how we define it. We just use this terminology, right? Psi of x. So I'll say psi of x. Psi of x is defined as a wave function. Okay. And for this wave function, pretty much what we have, right? That's how we define what a wave function is, right? So any particle moving along a wave, we say it's some sort of wave function, okay? Now, there's some things you need to know about momentum space and position space, okay? So let me have some nomenclature here that's important. I think I'm going to go through position space. So position space. Okay, so position space, psi of x. Okay, so position space psi of x. Okay, we'll call this psi of x, our wave function, and we'll talk about momentum space by another function called phi of p. Okay. Yeah. Okay, so you want me to move further down? Just give me a sec. I think I'll do that. Yeah, just want to make sure everyone else is understanding. Sure. Yes, we can do that. We can get to, I even had that in my notes. We might move down to that. Yeah, so Fourier series, right? Okay, so the connections between that. So Fourier series, pretty much. Just give me a moment. Okay, so let's get to the Fourier series. Okay, so Fourier series. Fourier. I'm going to use a different color here. Let's get to red. So Fourier. I'm going to say Fourier in general. Okay, Fourier in general. Fourier connections to QM. QM. Okay, so first off, definition of a Fourier series, right? Definition of a Fourier series is the following, right? F of x is equal to, let me see again, I always forget this, A0 over 2 plus the summation from n equals 0 to infinity of an cosine nx, there's to be parentheses here, plus bn sine nx, right? Where an cosine nx and bn sine nx. It's a trigonometric series. That's what a Fourier series is. So Fourier series is, first off, is a trigonometric series. So Fourier series is a trigonometric series. No, metric series. Okay. All right. So this hopefully is jogging some stuff. All right. So then we have that. And then from here, what's an and bn? So a0, an, and bn are coefficients. Okay. So the way to measure a0, you need to know how to measure a0. A0 is just taking, I'm trying to remember this. It's been a while. No, a0 is equal to 1 over 2 pi. Oh, yeah. Get rid of the 1 over 2 here. A0 plus. Yeah. Made a mistake there. So A0 plus the summation, infinite series. A0 can be calculated by doing 1 over 2 pi. 1 over 2 pi. Integral from minus pi to pi of f of x dx. F of x dx. Okay, an is equal to 1 all over, what is it again? This is 1 over pi. I am forgetting an integral f of x cosine nx dx. Yeah, 1 over pi integral from minus pi to pi f of x cosine nx dx. Bn is equal to 1 over pi integral from minus pi to pi of f of x sine nx dx. Okay. All right. So then we have this. Okay, so this is calculating the coefficients. Now, if you wanted to connect this to quantum, right? Because these measure pretty much any type of harmonic wave effects and stuff like that. But also it helps in QM as well. For instance, if you had a wave function, right? So example, right? Example, you have a wave function psi of x, right? So a particle moving along a wave is a piecewise function, for instance. Let me think of a piecewise function. Let's say you had psi of x equal to, why can't I think of a piecewise function off the top of my head? Let's say you had negative, let's say you had L over 2. Actually, no, X over, yeah, we can do X over 2 or something, X over 2. And limits of integration, we're going from, let's say L is between upper and lower bounds from minus, let me see here. Oh, sorry. X is between minus L to L. Doesn't matter. And let's say we had negative x over 2, and L L to, let's say minus L to L. Okay, any questions so far? Any questions, anybody? Let me know how's it going. Okay. All right, so let's get back to it. So we have this. So an example of this, right? In other words, a Fourier series can calculate the wave, how a wave function is operating on a piecewise function. And the wave function can be anything. It doesn't have to be a regular function. It can be a piecewise function like this. This is a classic example. Okay. And what you would do is, right, is you would just take the following, right? Right. So you want to calculate your A naught, your AN, your BN, right? So in this case, instead of f of x, your f of x is your psi of x, is your wave function. Okay, so you just replace it with the psi of x's, right? Does that make sense? Don't worry, there's going to be homework questions for those of you who are interested in challenging yourselves. Okay, so, and we'll keep up to date. I want you guys to have some really interesting homework questions if you want to try them. That will be the end of this live show, which will be somewhat soon. But yeah, because I have other things to cover as well. But I hope you're understanding how this will connect to these coefficients here. Okay. Nope. All clear. Is all clear good now? Okay, good. So I hope I clarified some stuff. So there's going to be homework questions coming soon. Okay. And we'll probably have a Friday. Okay, good. Excellent. We'll have a Friday get together on the homework questions, hopefully, and see where it goes from there. Yeah, I think Friday is good. Office hours will be Friday. Think about that. All right, so let's go to. Oh, I haven't shown the homework question yet. We're going to get to that. Yes. I just want to show you guys one more thing before getting to the homework question. Okay. All right, just one more thing before the homework question. It's only going to take 10 minutes and then we'll be done. Okay, it's going to be very interesting. How the Fourier transform connects to QM. Okay, so this is the Fourier series. I'm going to show you how the Fourier transform is going to connect. Okay. All right. But yeah, you can take this for a homework question if you want. Yeah, that's fine. I didn't have it as a idea for a homework question, but yeah, that's fine. Okay. But here it is. And now I'm going to talk about this guy right here. I think I'm going to talk about this. Let me think if this is appropriate. Yeah, I might do that. Key overlaps and plane waves. Okay, I'm going to go quickly. Yeah, Fourier transform and chains of bases. I'm not going to go through all the nomenclature, but as long as you know the mathematics, the physics will make sense. Okay, more or less. Yeah, Fourier transforms. So we're going to talk about Fourier transform. Transform. Forms. Connected to QM. Okay. All right. Yes, you're welcome. We'll go back over here. We're going to be looking at, yeah, I think we're going to do that. Let's see. Okay, so now we got this guy over here. We're going to look at, yeah, Fourier transforms applied to QM. I think we're going to start off with this. Okay, I mentioned something called momentum space earlier. At least you sort of got to see it. So momentum space. So momentum space. Momentum space. Okay. I talked about momentum space. You need to know what this is. Should I talk about it? Yeah, I should be talking about. Is in the notation. It's an inner product notation. Okay, and it's like this: P with the wave function. Okay, this is the momentum operator. This is the yeah, the wave function. Okay. Now, I'm not a complete expert in physics. My main thing is mathematics, but I do know the applications in quantum mechanics. So this will be handy for those of you who want to know the applications, how this relates to how Fourier transforms connect to quantum mechanics. So there's something called momentum space. So P and psi, that's going to be important. Yeah, momentum space, position space. Yeah, I wanted to talk about that, position space. And position space is just saying that x was psi. Okay, x for position, p for momentum. Okay. Any questions on this so far? Yeah, psi, Greek letter psi. Yeah, that's right. Also, anyone else have any questions in the chat? Anybody else? Anybody else? Don't be shy. I hope I'm making ground, because quite a few of you also have interest in the connection of Fourier transforms to quantum mechanics. We're doing that right now. Okay, let's get back. All right, so position and position momentum space I was talking about. And we want to compute a wave function. Yeah, we want to compute. We want to compute. We want to compute this. We want to compute a position. Let me think. What are we computing? We want to compute a position wave function. Position wave function. And a position wave function will be the following. Let me think again. What was it? P and X and P again. No, psi of X. Psi of X. Let me put this over here. Position wave function is going to be the following. Okay. It's just going to be psi of X is equal to X, and psi. This is just saying an inner product. Okay. Those brackets here are behaving as an inner product. For those of you have linear algebra background, it helps a little bit. If you know the notation, you don't need to have the linear algebra per se for this. But at least for what we're doing right now, it would help, but it's not like absolutely necessary. Okay, so now we have that. Now, what I'm going to do is, so we want to be able to calculate something called a position wave function. Okay, now what we need to know is what psi of X is. Okay, so I'm going to calculate the following. Okay, so I'm going to just go over here. Just 1 second. So I'm going to highlight this. So psi of X, by the way, psi of X is equivalent to the position wave function X with psi, and this is equal to the integral from -infinity to infinity. X, let me see here. X, let me think. XP, P psi, XP. Yeah, X, inner product of X with P and psi. Okay, and that's going to be with respect, differentiate with respect to P. Yeah, I was differentiating with respect to P. Just 1 second. Okay, differentiate with respect to P. Any questions? Okay, is that good? This is a formula that's important. Okay, I'm highlighting this as a formula. So important. Okay, so important. Note this is a formula. So I'll just say maybe a definition. So definition. So DEFN. Okay, that's the definition. Okay, so we have that. All right, so we have this. Okay, so now that we have that, okay, we're going to look at how do we deal with this? Does anyone know what I'm talking about, or are you lost? Sorry, someone is asking me something similar on my phone. No. Let me see. Anyone ask anything? You see anyone ask? All right. Any questions? Any questions at all? Moggers, you're lost. Where are you lost, Moggers? Hey, or is everything okay? I put this wave function momentum formula up on the board. Position wave function. It's a position wave function formula. That's what it is. Okay. I'm going to derive an expression here. Okay. I'm then aiming to derive something. Okay. First off, what I'm going to note here. Okay. So note, I'm going to substitute some really information. In other words, I'm going to derive a quantum Fourier transform. Okay. If you're lost. What was the last thing you did? Can you, oh, got it. So you're understanding the formula I put up. Thought you was not live for a moment. You lost track. So you understood the formula. It's a position wave function. Okay, so let's go back. So this is a position wave function. Now we're going to need to use this to derive a particular formula called the quantum Fourier transform. That's what we're going to do. So we're going to substitute. So we need to know some things here. First off, note. I always forget this formula. I haven't done quantum in a while. What is it again? As physics comes sometimes slower than math. Give me a moment. What was it again? We have to use the momentum, S.T.E.M momentum position operator. X P inner product is equal to e to the I momentum operator times x. Ix, I think it was over square root 2 pi h bar. H bar is Planck's constant. Okay, Planck's constant. All right. All right. So I'm going to substitute that into here and make my life easier. Okay, so we're going to go to page 5. Okay, page 5. Here we go. Okay, we're going to go to page 5. So now we're going to continue. So let's retrace our steps. Okay, no, that wasn't it. That wasn't it. Where was it? Yeah. Yeah, that's what we wanted to do. Okay, so e to the IPX. So we had x psi, right? So let's go and do that. All right, so let's go to the next page. I'm losing track of my pages. Where was it? Yeah, x psi. So we had x. So we had x inner product psi equals integral from minus infinity to infinity of x p. And then what do we have again? xp p psi. Yeah, xp p inner product was psi. And then it was dp. Okay. All right. It's times psi squared. Isn't it the psi squared, the statistical definition of the wave function? Let me see here. See, there's wave function psi. No, because this is the position formula. I think you're thinking of when we have this minus infinity to infinity of psi of x squared dx is equal to 1. It's the probability. This is the probability formula, right? Statistical probability, where a is small or equal to x, small or equal to b, and this is equal to this. Yeah, so it's not the same thing. Okay, I know it's very easy to get them confused in quantum mechanics. There's a lot of the formulas look similar. That's why I have to refer to my formulas that I have on the side, because they're very similar. It's easy to mix them up, so you have to be very careful. Okay, so we have this. Okay, so we're using this guy right here. I'm going to substitute my information so earlier. So substitute the following, that x xp, x inner product p is equal to e to the ixp, e to the ixp, so e to the ixp. So this is just saying that the position momentum space operator is e to the ixp all over the square root of 2. I always forget it. How do I forget that? For 2 pi h bar, square root of 2 pi h bar, 2 pi h bar, and I'm going to substitute into the formula above. Okay, so now I'm going to get this position space with momentum space is equal to integral from minus infinity to infinity. Xp is just e to the ix, yeah, e to the ixp power all over square root of 2 pi h bar momentum space with the wave function, the problem with the wave function, dp. Okay, any questions? Oh, you just learned them. When you mean you just learned, are you taking any elementary quantum mechanics courses, or is it just for what class? University, school, high school, university? I assume university. This is not. This is nowhere near high school. Is it for university? Just 1 second. Someone's messaging me something. Learn them. I get confused often. Yeah, don't worry. I'm going to clarify. I'm just make sure you understand the important differences here. Okay. All right. So now we have so I was just using the plane wave formula, right? So that's what this is. The x inner product p, the momentum operator, position space with momentum operator is the momentum space. Oh, that's impressive. Oh, that's very impressive. Physics, astrophysics Olympiad. Damn, that's impressive. For high school, yeah, that's impressive. Good for you. Yeah, it's good for you. Good. Okay, so that's why you're familiar with the notation that I'm using here. Because usually those Olympiads are very challenging. So they dig deep into university concepts, very deep actually. Sometimes third year concepts pop up. All right, let's get back to it. Good for you, by the way. Anyway, so we're going to go here again, right? So we have this guy. Sorry, someone is just annoying me here. Okay, so another thing here. Oh, go away. Oh, damn it. Sorry about that. Yes, this, right? Go away. Sorry about that. This would be represented. Let me make sure. I think the dp, I messed up something. Dp is d phi, e to the ixp power divided by root 2 pi h bar times the inner product of momentum space psi times dp. Make sure. Was it dp or deep psi? Just 1 second. I messed something up. dp deep psi. Yeah. Okay, have that. 1 second. Someone's giving me a figure. Oh, yes. This here is phi of p. Yes. Remember earlier I said that phi of p is p inner product psi. This is phi of, yeah. So this can be represented as phi of p now. So I can get rid of this and say this is phi of p. Okay, so this is now phi as a function of momentum with respect to momentum, right? Okay, so now we have this guy. Okay, does that make sense? Because that part was just the phi of p. Okay, so that was my phi of p. Just 1 second. Okay, and then from here now, right, so I got my phi of p. I was going to do something else. Now, what is phi of p? What's phi of p equal to? Does anyone know what phi of p is equal to? Anyone have any guesses what phi of p is equal to? Knows what it is, can connect it to something. Well, phi of p, right? So now we know. So now we can say that, now I can say that phi of p is equal to the inner product of p momentum with the wave function, right? And this is equal to the integral from minus infinity to infinity, right, of p inner product, what was it again, p inner product of x, 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 x inner product was psi dx. Yeah, dx. Any questions? What about Euler's function? What's Euler's function? Did you want to know? Oh, what I just wrote. That's Euler's function. Yeah. Yeah. It has to, yeah, it has to do with that. Yep. Okay. All right. And then from here, what we're going to do is, okay, so we've got that. Then from here, what I'm going to do is this. I'm going to take this integral. Okay, I'm going to take this integral and do something interesting with it. What is this integral equal to? Make some connections upstairs here. What is this integral also equal to? Anyone have any ideas? What is this integral equal to? Oh, I'm aware of that. Yeah. Yeah. No, they don't. Yeah. Yeah. I think you will enjoy, you may enjoy my book. You should check it out. Because it has a lot of advanced concepts of like advanced calculus but in not only just math itself, but applied in other areas of physics and engineering. Oh, perfect. Yes. Yeah. Yes. Here's my link. Yep. It is STEM1online.com/books. Preferably the ebook. Paperback is takes longer to ship, right? So I'm assuming you want the ebook. The ebook is cheaper than the paperback, by the way. So if you're interested in the ebook, that ebook would be probably a better idea. It's cheaper, so $25 or $30. I forget what it is. Yeah, but yeah, you will have it's going to teach you a lot of stuff. Okay, yes. So check out the link, and yes, it's on my website. Okay. All right. So, oh yeah, you'll learn a lot of stuff in there. It has it has applications of integrals. It has like it builds from basic to more complicated to very complicated. So as long as you have that knowledge from all the way up, you can build up on your knowledge, right? So we have that. Okay, and also, so it's for those. It does have. Yes, of course. Yeah, all these problems are in the book. Either they can be they haven't been solved, or they've been solved in the examples or whatever, right? Okay, but yeah, it's for two types of students: students who want to build their knowledge in advanced integration, right? And so number one, number two, those who want to do that and have the applications, see the applications as well. It has a lot of applications, there's applications. And number three, if you want to tackle open-ended problems. Those problems are so tough, not even I can solve them. What that means is they don't have an answer. I put them in the book as well. So there's a section for open-ended problems, but they're so tough, no one can solve them. So if you like challenges, if you like to learn advanced mathematics, this is the book for you. All right, so let's get back to it. So we have phi of p is equal to this. Now, this is actually equivalent to this minus the integral minus infinity to infinity of x. Let me see here, x psi. Let me just write that, sorry, that e to the I. Yeah, because remember what this is equal to. Remember what this is equal to. X inner product of psi is just equal to the following, right? It's equal to this. Okay, so I can substitute that in. So now it's minus integral from minus infinity to infinity, p inner product of x. Okay, so p inner product of x, integral, right? Integral from minus infinity to infinity of e to the I x p power all over root 2 pi h bar times phi of p, derivative of momentum. Okay. Any question on that? International IOQM. That's right, IOQM. Can you tell me what I mean? IOQM. Anjali Mishra, who can you tell me a bit about yourself? Do you have background in integral calculus and linear algebra, first off? And I hope you're interested in mathematics, specifically applied mathematics. That's what I'm talking about from my book. High schooler. Okay, what grade? Or I am, oh, International Mathematical Olympiad. Yeah, so trust me, this there's a section of it that can test your wit, your mathematical intuition. However, though, yeah, that's right. It's not exactly for IMO, but it is challenging. Yeah, yeah. So Andrew Mishra just mentioned that it's not for IMO, but it is. The level of rigor is the level of intellectual understanding that you need to have is very high, though. So I mean, you can use it as a side thing for IMO, but it's not like the IMO. The IMO will be like algebra, number theory, and etc. Okay. Okay, Angie, you've studied calculus. Good. All right. All right. Good. But it can be a good a tool on the side for IMO if they give like there was once, because I've done IMO, not mine, not when I did it, but there was a year when someone did it and there was like like maybe a calculus question here and there, but it's not exactly comes up in the IMO. It may happen that they have a calculus question. It may happen to be integration, but not exactly. No, IMO is algebra, number theory, combinatorics. Angie, yes, we're going to get to it. We're going to get back to it. Just like Mongers. Mongers is interested in doing this. Yeah, exactly. Yeah, exactly. Yeah. However, I'm also working. I'm also working on a book on IMO problems. Takes a while. I need to refine it, but I'll keep you in mind, Mongers. But this this book right now is just it's extremely well preparation for university and college, right? So you'll be able to get all the way. If you do this book, you should be able to get to third year, fourth year university. Yeah. That's what I'm saying. Like in IMO, you'd be lucky to see this. That's what I was saying earlier. You'd be lucky to see happen to be a calculus question. Putnam, though, will have definitely will have it. I think that's what. Yeah, that would be more appropriate. This book would be for Putnam. Mm-hmm. Yeah, this book will be for Putnam for sure. At least the open-ended section of the book specifically, where you have unsolved problems that require very detailed, rigorous research and stuff like that. That will be Putnam or yeah, Putnam for. And then there's another one called Switzer, which is even harder than Putnam. They only do it in Hungary. It's a Hungarian math contest. Jesus, it's just too difficult. Yeah, too difficult. Yeah, very difficult. So this book would be appropriate for a Switzer contest, and or Putnam more than IMO. Okay. But I hope you'll be interested in getting this book, because in the long term, this will help you get through university. Okay. All right. So let's get back to it. So while I was doing this, I substituted what was it? My plane wave formula. Plane wave formula is this, by the way. I didn't talk about in detail. This is the plane wave formula with a combination of momentum space and position space. And I substituted into my integral inner product of the position operator with the psi operator. Okay, and then I got this. And then this can just be written as the integral from minus infinity to infinity. Okay, that's 1 second. Someone's contacting me. My apologies. Just 1 second. Yeah, so this is just e to the, this is 1 over square root of 2 pi h bar, right? 2 pi h bar e to the ixp power, right? X is the momentum, position space, p is the momentum space. Okay, e to the negative ixp. I'm just getting that e to the negative ixp. Put a negative here, make sure you put negative. Okay, and then it's psi of x dx. Okay, and this happens to be something called a QFT. This is, so we've proven, or I should say we have derived. So this is a derivation of something called the quantum Fourier transform of a quantum Fourier transform. Okay, and that is it. Okay. All right, so that's it for today, guys. This was a long live show because this turns out today I had a lot of people come in interested in advanced applied mathematics. That is it for today because I am exhausted. Actually, there is one more thing. I promised homework questions for those of you who like challenges. All right. Oh, thank you, modders. Thank you. I appreciate it. I'm glad that you're finding this interesting. Yes. So, as I said, I hope you like and subscribe. I hope you check out the book. And I also hope, more than that, that Friday, look out for me Thursday or Friday. Friday for sure. I think we'll do office hours. In the office hours, I might take up any of the homework questions I'm going to put up and then continue with the new stuff. Okay, so let me go over here. So I'm going to just choose a homework question from this. All right, let's see here if there's a homework question. Just give me a moment. Let me just stop sharing for a sec. Stop sharing. Yes. I think, are you in India or any of the Southeast Asian, any of the Asian countries? I think it's the time zone difference there, major time zone difference. Yeah, I assume so, based on the time zone. Yep. Okay. All right. That's good to know. Now for me, it's still Wednesday. 1 hour until it's Thursday. Wait. I'm going to put up a problem. Just give me a sec here. I want to see if it's appropriate. let me just take a picture of this. Yeah, this one was one I wanted to look at. Just give me a sec and we'll put it up. Okay, I think, yeah, this one is going to be good based on what we talked about today. Okay, so here's a challenge problem. Okay, let me just, yep, yeah, conic sections, stuff like that. Yep, I graduated university, so yeah. Anyways, let me put up the problem that I was going to put here. So we're going to look at, so here's the homework problem. Catch me on Friday to discuss the homework problem, for those of you who want to do it. Okay, so challenge problem 1. Okay, here's challenge problem 1. I want you guys to prove the following. So prove, let's see, prove the Fourier transform. Yeah, let me put it here. So I'll say prove that the Fourier transform, the Fourier transform of the function f of x equals e to the negative a absolute value of x. You guys should know what an absolute value of x is the following Fourier transform. I'm going to highlight it. Is equal to this Fourier of f of x, yeah, f of x as a function of omega, because a Fourier transform is just going from x space to omega space, right? So Fourier transform is equal to 2a divided by a squared plus omega squared. And there's a hint. Express, so I'm going to express the following. Express e to the negative a absolute value of x as a piecewise function. Okay, as a piecewise function, and split the integral. Okay, and then relate it to the integral from 0 to infinity of e to the negative ax cosine omega x dx, please. Okay. And that is the challenge homework question. Okay. Any questions? Oh, no, damn it. My apologies. Let me just get back here, screen share. And where was it? Yeah. Just give me a moment, entire screen. Just give me a second. Okay, I'm going to go to the whiteboard. Can you see it now? Were you able to see it? Right here. Here it is. Okay, perfect. So here's the challenge problem. Everyone in the chat, this is the challenge problem. And I think Yeah, so here it is. So prove that the Fourier transform of the function f of x equals e to the negative a absolute value of x is the Fourier transform, this guy here. Okay, pay attention. This guy here is equal to 2a all over a squared plus omega squared. Okay. All right. Just going to give you some time to copy it down. Okay. And the hints express e to the negative a absolute value of x as a piecewise exponential function. So say exponential. So piecewise exponential function. Okay. And then what I want you to do is split the integral and relate it to the integral from 0 to infinity of e to the negative ax cosine omega x dx. This is a challenging problem. Okay, so try doing it. This will be for homework, okay, because I got to get going. All right. Moggers, good for you. I'm proud of you. All right. The mod. What do you mean? The mod. You mean modular arithmetic? I'm understanding. Can you explain what you mean? I'm understanding exactly. Yes. Yeah. The modulus will be a. I don't know if the modulus will be a problem. I want you to figure that out. Misra, yes. Is there any relevance of it? Of course there is. Yes. All of what I've been doing today has been applied mathematics. Right? It is less. It's. Yeah, exactly. Exactly, guys. Yep. All right, good. I will be on either tomorrow or Friday. No, in context of conics. Oh, that's what you mean. Is there any relevance of it in applied mathematics? Yeah, yes, and yes. At least the integration part. If you're relating it to Kepler's laws, right? If you do one of Kepler's laws requires conic sections. Is related to conic sections, at least ellipses, parabolas, and all that stuff, hyperbolas, based on different types of eccentricity of the parabolas and the hyperbolas, right? If you're familiar with that, they're mainly polar conic sections with different eccentricities, but that would relate to integration. It's very much good. Yeah, I think Mausers is understanding what I'm saying. Integration used in Kepler's laws, and that's an application of conic sections. All right, you're very welcome, all you guys and moggers, definitely for sure. I hope you'll catch me either Thursday or Friday. It's gonna be roughly same times. Usually I do 2.5 hours, not 2 hours usually, but yes. All right, Mister. Bye. Hope you like and subscribe. Moggers, you can always let me know more information on the book and how you can purchase it. Have a great yes. I will see you later. All right. Bye for now, guys. See you to the next live stream.